likely to be here?
Yeah, good point. So I guess we're right on time. So echo will be here for your regular class at 7:30. We're going to do a full echo lab. So that second protocol we're going to do. So we're pushing off, if you haven't got the note, we're pushing the protocol test until Monday morning lecture. We'll do that very first thing. We'll take the test and then turn it in, and then we'll continue on with the lecture. It'll be easier that way to get everybody at once. So vascular gets to sleep in.
Yay.
Don't say I never thought of you guys. We'll be thinking of you all morning Friday morning as we're struggling through echo. Okay, so today I want to wrap up our discussion on systole. We'll go over some of these formulas on the ends. It won't take very long, and then we're going to hit up diastole. So I did record diastole already. Has anybody watched it yet?
Yes.
Is it not glitchy?
Actually, it was fine for me.
Okay.
When did you do that? Because I checked day
Last
before.
night.
Yes. Oh.
Yeah.
Okay.
It was a late night. Had to do my daughter's, she had to do a Panopto presentation for an English thing on the screen. So we did that like 5 times. And she still pronounces like Queen Latifah instead of Queen Latifah.
Oh my goodness.
Yeah.
Sounds like an
There's several
presentation.
old names and stuff that she totally butchered.
Queen Latifah's now old.
She was the youngest one of the people that she was talking about. So Bessie Smith is the old jazz singer that she was doing a presentation on. It was fun. All right, so systole. Cut these lights down. So my attempt is going to be to record on video the board. So, but it'll have to be put up on YouTube. So. It may work, it may not. We'll see how it goes. So don't rely on that per se, but we'll give it a shot. Turn this up. So let's go over the components of systole first. So CSA, what does CSA stand for?
Cross-sectional area.
Cross-sectional area. What is the formula for a cross-sectional area?
Is that the area of the annulus of the aorta?
Yeah, so a cross-sectional area can apply to anything, any cross-sectional area, but particularly, most often we look at the aorta. So, due to a couple of formulas, we usually calculate the LVOT area. So we need a cross-sectional area, we need to find the flow that goes through the LVOT, because that helps us to determine stroke volume and cardiac output. So, somebody want to come up and write on the board the formula for cross-sectional area? No, you want it. It's not recording. All right, what is it?
0.785 times d squared.
Okay. So cross-sectional area, why is it, so what is the mathematical area for a circle? Okay, so the reason this is 0.785 is because it is normally pi r squared. This 0.785 is taking in consideration pi and the fact that we're using a diameter instead of a radius. Okay, so this is basically an area of a circle-ish, but because we take a diameter in echo, we're not taking the radius of it. That's why we have that. So with the aortic valve, we'll take, well, let's take, sorry, not aortic valve, let's take the LVOT. What does LVOT stand for?
Left ventricular outflow tract.
Left ventricular outflow tract, good. So, so that equals, just FYI, and I talked about this in EKG, anytime you're doing mathematically, always write your zeros before the period, especially if you're writing up your own handwritten reports for the doctors. It's very easy to miss a written decimal, you know, so The 0 in front of the decimal really helps to emphasize that. So that times the diameter. Now the diameter on an LVOT area is, they like us to use 2 for the most part. There will be some doctors never do anything but 2. And the reason being is that if you mismeasure it, you're squaring your error. Okay, so it increases the error significantly. So some doctors will use only 2 centimeters and then square it. Okay? Calculate that out for me. What does that come out to? Calculators? I can do math, but you know, I like calculating.
It's 3.14.
What is it?
3.14.
3.14?
Right.
It's pi.
Yeah, that's what
I like pi.
Phil Nerdy is like, it's pie.
It's pi. So that is the normal cross-sectional area of an LVOT area. Okay, so 3.14. What are our units in this?
Centimeters.
Thank you. So centimeters squared. Remember, this is an area that we're talking about. All right, so this is going to be important to put into our formula. So whatever measurement you take, I am personally a believer that when I take an area or a diameter or something, I like to measure what I actually see, because is everybody's aortic or LVOT area, is that always 2 centimeters? No. It does vary. It is important for us to make sure that we're in the exact center of our object. If we're off to the side, we're going to underestimate what it is. Or if we've obliqued the measurement or the image, then we're going to overestimate what it is. That's where the error comes in. So again, some doctors will always, and techs likewise, will always go to 2 centimeters for that. But a little 80-year-old lady that's about 4'5" is not the same as somebody who's 6'7". Okay. A pediatric patient is not going to be the same as an adult patient. So just keep that in mind. I like to personally measure what I actually see, provided I got the best image that I can. So that is the cross-sectional area of the LVOT. The next one on there is stroke volume. Okay, now the LVOT area is not going to give us the systolic function in itself. We have to do the rest of this to determine systolic function. Which is why it's on systolic function. Okay, so what is the stroke volume formula?
Heart rate times cardiac output, or heart rate times stroke volume? Oh, no.
Nope, that should be cardiac output.
Is that the CSA times VTI?
I cannot write this one. Yes. So CSA is again cross-sectional area times VTI. So the stroke volume in that specific area is the cross-sectional area of that area that we just calculated. Now presumably we're going to go with LVOT here, but I could be doing this on aortic valve, I could be doing it on any other area. The theory is whatever goes through one area must go out another area if we got a closed loop system and my valves are working properly and it's not allowing backflow and stuff like that. That's why we're looking at this. So cross-sectional area times the VTI. What is a VTI? This is important to know. Velocity time integral. Some people may call it TVI, which is time velocity integral, same thing. And what is where do we get that from? So we know where we get the cross-sectional area from. So first of all, I can't measure the stroke volume unless I've got the cross-sectional area. So what is an important thing that I have to have before I do it?
Apical 5J.
I got to have this. So we got to get the LVOT diameter. First of all, where do we get the LVOT diameter from? So we got 2 centimeters. I mean, we can just make it up, because some people do. But what image do we get in echo that gives us the LVOT diameter? Draw it out.
Long axis.
So parasternal long axis. Okay, so parasternal long axis, we're taking this, we're we're taking this just before the valve, okay, just before the annulus. Okay, I'm not actually measuring the annulus of the aortic valve, I'm just before that point. It does have to be perpendicular to my dimension, okay, and that's where it is. It's inner to inner is the measurement on this. So that's the LVOT diameter.
So like when you have your cursor, like do you put the top of the cursor at the center or like one of the endpoints?
So where it crosses, kind of the crosshair area, that goes on the inner side of the wall, just to the inner side of the wall. The only ones that really have to be leading edge to leading edge, where it's identifiably different, is the aortic root and the left atrial dimension, both in 2D and M mode. Okay? So LVOT diameter comes from that. So on echo, one of the things that I have to get when I get an echo is this. Okay, if I don't get that, I'm not going to be able to calculate the stroke volume or valve areas or anything like that. So, so now back to this. Then what's the, so a time velocity integral, so you guys that have done your reading ahead of time, which is everybody of course, where do I get my VTI from? What is it?
Apical 5-chamber tracing.
Okay, so it's a tracing of the spectral Doppler in apical 5 chamber, which is correct. That can also be done in apical long axis or an apical 3 chamber view. So, which is essentially this, just up on its end. But the 5 chamber I'll just draw out. Let me just open that up. Okay, so here's my aortic valve here. Mitral valve kind of comes in here. So I've got the 4 chamber with the aorta, or the 5 chamber view is another name for it. RV, RA, LV, LA. And the main thing that we focus on is getting that aorta open. That's the most important thing. So this is again taking my apical 4 chamber view. So indicator is in the apical position, pointed toward the floor and slightly up behind the shoulder. So it's kind of twisted counterclockwise slightly. And then tilted anteriorly, sweeping your beam anteriorly towards the chest wall to open that up. Okay. Once we've got that, we're going to take our spectral sample perfectly in line ideally. So my transducer will actually be slightly lateral to the heart to get this, but my area of interest is right here. Okay, so my spectral Doppler is going to be there just before the aortic valve. In theory, when I do these measurements, where I take my sample needs to be exactly where I do my measurement. Because that changes shape very quickly after that, and it can significantly throw off your calculations. So what does that look like on Doppler? So in echo, again, we always keep things the BART protocol, so blue away, red towards. Anything, it's either coming toward the transducer or away from it on the spectral Doppler. So my flow going out the aorta, is that coming towards or away from my transducer? It goes away from it. So my flow for the LVOT is going to be look like this. Okay, it is pulsed wave, so I should have somewhat of an envelope flow. It should not be totally filled in. So my LVOT Doppler is going to look like this. It should have, if we're in the center of it, it should be fairly sharp borders to my Doppler. And then the VTI, all it is taking a tracing of it. So you will want to enter that into the calculation package, because if you don't, you're going to have to hand calculate all this stuff, which you really don't want to do. Not incredibly complicated, but it is required. So I'm tracing from the baseline all the way around. So I'm just tracing the outer profile of that waveform. That's what a VTI is. It doesn't matter if we're talking about a mitral valve, if it's an aortic valve, an LVOT, anything that I do and I'm looking for a VTI is just a tracing of that waveform. Some of the ultrasound systems will actually automatically put that out there for you. So like the P5, for example, sometimes when you freeze an image like in vascular, it puts up 2 lines where the cardiac cycle is. and traces everything in between it automatically. So it may do that for you. A lot of these measurements we're going to do by yourself. So you're going to get used to tracking with a mouse, a track ball around the outside of that. So that's how we do a VTI. So it's just a tracing of the waveform. And this one happens to be of the LVOT. Okay. Anybody know what the units are for a VTI?
Centimeters.
It is in centimeters. Good. So we're going to take our formula from up here, so the stroke volume for this LVOT, and if you're notifying an area, you can notify it just by a sub notation here. Subscript down below the thing that it's measuring. So these are all LVOT. That will be important later as we talk about aortic valve and calculating the area of an aortic valve. We have to algebraically go through and determine what it is because we don't have all of the pieces of information. We're using algebra to find it. So if I was doing an aorta, this would just be like AOV for aortic valve. And then that will help you distinguish what's going on. So cross-sectional area, stroke volume of this. So I've got, I take my 3.14 that we calculated from the cross-sectional area. Okay, and then times that by whatever VTI that we acquire here. So give us a number. Is there a number? Somebody have a book in front of them? You're not necessarily going to memorize what a normal LVOT VTI is. 18? Okay. So we'll call that 18. Good. So these are both centimeters. All right. So, and that one's centimeters squared, by the way. So what does that calculate out to? 56.52. Okay. All right. So I've got centimeters here, centimeters here. What is my units on this?
Centimeters cubed.
Okay. So we're looking at a volume. Is that appropriate? Okay. So the area is at centimeters squared. Centimeters cubed is the same thing as milliliters. Okay. So usually when we're calculating cardiac output, we're actually looking for it in liters per minute. In this case here, this would be the same thing as milliliters. If I was going to convert that to liters, what would that be? Okay, so we're going to move it over. So what is it, 0.56? So if it was liters, I would just convert it to that.
0.056.
0.0, yeah. Sorry. Okay, so if you're going to calculate that out, that's what it is. So the fluid of this heart then with a 2 centimeter LVOT diameter and a VTI of 18 centimeters is going to give us that. Okay. On my test, I'm not going to have you necessarily calculate this, but I do want you to know the formula. Could they have you calculate it on registry? Absolutely. Okay. The measurements that they usually use on registry are not something that you would require a calculator with, so they'll usually be pretty simple, fairly rounded numbers to work with. Okay, so you can be able to do it on paper. But want you to know how to calculate that out. So does that make sense on stroke volume? So the two pieces of information I need to calculate a stroke volume in the heart is what? So I need the cross-sectional area, so I need peristernal long-axis view with that measurement, and then I need my 5-chamber view with that Doppler through the pulsed wave Doppler through the LVOT area. Okay? Just to emphasize otherwise, if I am looking at calculating the aortic valve area, which is often what we do in echo, and I wanted to find the stroke volume through the actual aortic valve, it should be the same because whatever went through the LVOT should also be going through the aortic area. If I was to calculate that, I would put a continuous wave through the valve because it's not as site specific. We're going for maximum velocity, and that is the highest velocity in that area, or it should be. So I would use that to get the valve area, and I would trace it to get my VTI from that. And then I need a valve area. Now the aortic valve opening, is it nice and circular shape? No, it's triangular shape when it's open. So it makes it a little bit more complicated. So in the aortic valve, which is why we use the LVOT when we get to that section, we actually have to use algebra to find that out. So what they'll usually do on a test, if you're going to look at the aortic valve area, they would give you the stroke volume, and then they would give you the VTI, and then you'd have to do algebra to find out what that valve area was.
I'm just confused, why did we cube it again?
Why do we cube it? We're looking at a volume.
At a volume, and
So
then,
stroke volume is what we're going after. That's how much volume of blood is going out that area on that beat.
is that milliliters over liters? I just don't.
So, sorry if this got confused. It's going to come out as cubic centimeters
Okay.
For what our Doppler measurements are going to be, which is the same thing as milliliters.
Okay.
When we look at doing cardiac output, that's usually expressed in liters per minute. So you would have to do a conversion to make sure that that's accurate. Does that make sense? Okay. All right, and don't worry about that conversion right now. Just know that that's what it would normally be reported in. So that is stroke volume. Now to get the cardiac output, so that the stroke volume tells me how much blood is being injected on that one beat. Okay, so it's also important that we're consistent on that. So cardiac output, what's the formula for that?
Stroke volume times heart rate.
Okay. And I'm writing the annotation here of LVOT just because that's where we're taking the measurement from. All right, where do we get our heart rate from? So the piece of information we already know, because we calculated all this, is the stroke volume. So in this case, we'll do this in liters per minute, just because. Okay, and our heart rate would be whatever the patient's heart rate is. Give me a normal heart rate.
60.
60, 70. We'll say in this case it's 60, and that is expressed in
Beats per minute.
Okay. So a cardiac output is expressed in liters per minute. Okay. So I don't need the beats on there necessarily, but we are going to be doing this. Remember, the beats per minute is really written minutes is a denominator, so when I multiply this out, I end up with liters per minute. So what does that calculate out to for those with a calculator? 3.4. So in this case, it's 3.4 liters per minute is how much the heart is putting out at 60 beats per minute. Calculate that out as if it was 75 beats per minute. You do that for us. Yep. So that would be 4.2 liters per minute. So you can see the difference it can make just based on the heart rate. So that's properly how to measure that. So this is all based off of the LVOT area in this case, but it could be the aortic valve, I could be doing the mitral valve, any other section in the heart. Okay? So that's how much is being put out on the left heart. And again, theoretically, whatever went through this LVOT area is also going out the aortic valve, is also the same volume that came through the mitral valve. Okay? Any questions on that? So poor systolic function, since that was what we were talking about, if I've got poor systolic function, what would I expect to see?
Increased cardiac output.
Okay, so it would be decreased. So if it goes significantly low, then that's what we'd be seeing. On the LVOT stuff, if I've got a poor functioning aortic or a poor functioning LV, it's trying to squeeze in but can't squeeze in very well. It's sluggish. It might be slow. This is presumably going to be smaller. Okay, if I've got kind of a hypercontractile heart and it's really pumping out, I would expect that to go up. Okay, so it's going to be all relative to that. This LVOT diameter doesn't really change much with systolic function. It's just an important part of the calculation. You have to have that. Any questions on this? So that puts us through cardiac output, stroke volume, cross-sectional area. So all we've got left now is dP, dt, and tissue Doppler, the S prime wave. So I'm going to erase all this. By the way, I'm sporting the Echo Club logo if you guys end up wanting to get t-shirts with that on.
We wanted
Scrubs with that, yeah. Hats.
We ordered them, we thought you put it through.
You ordered them?
Yeah, we gave you an envelope full of cash.
I did not get any envelopes full of cash, let's be clear. All right, so what is dP/dt and what do I need to do it from your reading?
The amount of time to achieve a certain pressure? Or
Yes, it is.
I don't know.
It is the amount of time to take a certain pressure. This is going to be the waveform that I have to get this. I cannot do this without it. Is a mitral regurgitation. So that's going to be taken from 4-chamber view. Okay. 4-chamber view. It is going to be at the. It's going to be a regurgitation, so it's going to be coming through there. Let me just draw out what a regurg would look like. If I've got a systolic thing going on, my mitral valve is leaking. Okay, it's supposed to stop the flow so that it goes out the aorta. If it leaks and allows a backflow, what is that going to look like on my Doppler? What color will it be in? If we use the BART convention, which is blue away, red toward. It's what?
It'll be red. Regurgitation.
You said blue? Yeah, that's right. Yeah, it is blue. It would be red going, or sorry, it would be blue because it's going away from the transducer, which is up here. Let's just do this. So transducer's up here. We're looking at this spot here. The valve's supposed to shut when it goes out. Dropping this all over. We're going to put our continuous wave Doppler right through the center of that. But this is going to be a regurgitation that comes back into the chamber here. It will be all filled in. That's what a leaky mitral valve will look like. So again, to get the dP/dt, you have to have that to calculate it. So we're running our caliper through there with continuous wave Doppler. Yeah, let's draw the Doppler.
And what does dP/dt
Stand for?
like, what does it do? Again, I didn't hear the definition.
It's the change in pressure over time. And we're going to explain in a second why this is relative to systolic function. Okay, so this is going to look like usually something like that. It's more parabolic than an LVOT was. Remember, LVOT looks more like this. It's a little bit peakier, so to speak, than this is. These are typically more parabolic. These are intense waveforms. This is fairly hazy. You usually need to increase your gain. It's continuous wave, so there's no enveloping per se. There's a lot of turbulence and stuff in these jets in particular, which is what it's made up. It's a big aliasing type of a jet that comes back. Okay? And what we're looking at on this is it's been predetermined on dP/dt, the pressures that we do it. So our job is to take a nice envelope of the jet through the middle of the jet at 0° angle. Okay? And we're supposed to set our calipers at, this is 1 meter per second, or yeah, 1 meter per second, and 3 meters per second. Okay, so we simply put our caliper at those exact levels in the calculation package, and this is automatically going to use a Bernoulli equation to determine the pressure change from 1 meter per second to 3 meters per second. Okay, so our job is to get this and to place the calipers. The part that we're determining that we don't know is how much time it takes to go from this point to this point. So time is really what we're after in this. because as long as we set our calipers correctly, we've got the pressure changes. So incidentally, with the pressure change, what is the Bernoulli equation, simplified Bernoulli?
Pressure and velocity are inversely related.
So we're calculating the pressure based off of velocity, and this is 4 times the velocity squared. Okay? So if I take 1 meter per second for an example, when I set my caliper there, what is the pressure at that location? So that's 4 millimeters of mercury at that spot. What is the, if we use the 3 meters per second, which is predetermined, so square your 3 first, and then times it by 4.
36.
So we're looking at a pressure change of the time it takes for it to change from 4 meters per second to 36 millimeters of mercury. 4 millimeters of mercury to 36 millimeters of mercury. Okay, so what is the thing that we don't know?
How long it takes?
The time. Did I mention that before? That could be important. So that's really what we're looking at. We just have to set our calipers properly. It uses Bernoulli to find this. Looking at that pressure change, and time is what we're, that's the component that we don't know. That's the rest of it's kind of constant as long as we set it up correctly. So first of all, what jet do I need to see? Mitral regurgitation. If I don't have that, I can't do this. So what is it telling me? If I've got a regular systolic function, I've got a normal waveform looks like this, okay? What if it's a very poor functioning heart? Okay, a poor functioning heart, we're looking at how fast this occurs, and this is the area that I'm in. We may get velocities down. In a mitral valve, we're going to get velocities around 5 to 6 meters per second. That's 500 to 600 centimeters per second. That's fast. If I've got something pushing really hard against that, do you think that's going to go faster or slower? It's going to go faster. So if it's poorly functioning, it's going to take longer for that to occur, right? So my dPdt, the time factor is going to change as we go through that. So if I'm looking at that slope and I've got a poor functioning heart, it might look more something like that. Okay, so it takes longer to go from that 1 to the 3. Okay, so the time factor there is going to get bigger. And being that the time is on the denominator side, it's going to be an inverse relationship. Okay?
They're both, say that again?
dPdt is literally written like this. So this is the pressure on top over time. Okay? So that's the concept, is that it's the time that we're going after, it's that slope. We have to have the mitral regurgitation to do it. If we don't do it, we can't. So what is this telling me? This is telling me how, this is just an indication of how much squeeze there's going on in the heart. That's why it's a systolic function thing.
So it's taken from just inside the valve, from the atria?
Yeah, it's through the valve with continuous wave, but it is on the inside of the valve, on the atria side of the valve, because the leak is not on the LV side. Okay?
Why are you saying time is unknown? If we're putting calipers at 1 and 3 seconds, we know exactly how much time is between 2 points.
Do you know how long it takes to go from here to here?
Well, between 1 and 3 seconds is 3 seconds.
No.
I mean 2 seconds.
It is not.
What do you mean?
So that's
Meters per
this is
second.
centimeters per second or meters per second.
Right.
Okay, so it's not this here, but we're trying to determine what the slope is.
So that's essentially the last.
The slope is the time factor that we don't know. We know the pressure. It's the pressure change from that to that.
When you say poor functioning heart, you just mean like more poor functioning than the other one? Because right, the other ones, if you need mitral regurgitation, it's not technically.
So if I've got regurgitation, that just means the valve's not working properly, but the systolic function could be working perfectly fine. This is a reflection of systolic function of the ventricle. Okay.
So
with that.
The systolic function doesn't have anything to do if we have mitral regurgitation or not. That's a valve thing. But we can only do this if we have that, because you're not going to get anything if you don't.
So with that slope being delayed as it is, that would be represented in milliseconds?
Yeah, the time factor would be milliseconds.
Okay.
Okay, so that's just the concept. It's a systolic function thing. We're just looking at the reflection of how well the LV is functioning. That's, in essence, what DPDT is. All right, next one is
Wait, so we don't figure out the time?
you're determining the time by doing the measurement.
The calculation package will do it for you.
Oh.
Yeah. So it's like M mode. If I took a horizontal measurement in M mode, that's a time factor because I'm going from one moment to the next moment. Spectral Doppler is the same thing. As we drag across the screen, that's the x-axis is time, whereas the y-axis is velocity. And in this case, we convert it to pressure.
What's the normal time? What it should be.
What's that?
What's the normal time?
What is the normal time, does it say in there?
1200.
Say it again. So that's not the time, that's the full calculation. That's dividing the pressure by that.
Greater than 27.
Okay, so 27 milliseconds. Okay, I don't need you to necessarily know the time, I just want you to know the concept. Okay? And what the formula is. So that is DPDT. What about tissue Doppler? How do we take our tissue Doppler? From what view? If you said it before, that is correct. I don't know how you got that. Because you read the book. So where do we take our tissue Doppler?
Lateral and septal.
Septum.
Lateral and septal walls. Yeah, I'm just trying to throw you by the apex. So we're looking at the annulus of the mitral valve, so we're going to Doppler it in there for the septal and in here for the lateral wall. Okay, I'm simply taking my spectral Doppler sample through there. What mode do I need to use for this? If it's range specific, meaning it has to be at a specific depth, do I want to use continuous wave Doppler or pulsed wave Doppler? It has to be pulsed wave because it's range specific. It has to be right at that annulus level. Okay, if I've got that, can I use regular Doppler settings in pulsed wave? Because normally we're looking at blood flow, which kind of has to be amplified. If I take a sample, so what happens if you're doing a carotid study and you accidentally get it on the wall? Is it intense? Is it less intense than your blood?
You get a heavy wall.
It's more intense. So yeah, you can't, it's a pulsed wave function, but it has to be specific to tissue because tissue is very intense when you hit it with your Doppler. So you got to use the right mode. So it's usually, it's either DTI or TDI, depending on the system. Again, Doppler tissue imaging or tissue Doppler imaging, they're interchangeable depending on the vendor. Okay, so it's specific to tissue Doppler. It's got a bunch of filters and stuff set appropriately for tissue. So when I take my sample here, what do we look like? Did we talk about this already? We did, I think, once. Okay. So it's going away from baseline, so you can imagine the systole as it's going on here. If it contracts, are the annulus going to move towards the apex or away from the apex? So squeezing comes towards. As it relaxes, it goes away. So away is diastole, so if I got two little waves like this, these are my E and A wave, or more appropriately E prime, A prime, and this is S prime. Okay, so my S prime is the systolic component. So this is really systole. This section here is diastole. Okay, so this wave is indication of what my systolic function is. The E waves aren't relative to that. Okay? So what we do is simply, and not everybody does this, but you can, you simply measure the height of the S wave. That's it. So the bigger it is, the more movement there is, the better the systolic function. The smaller it is, if we've got a good angle, the less that my LV is functioning. It's got poor function. Okay?
Do you just measure from the peak to baseline, or do you do?
You'll just stick a caliper on this, which presumes it's from the baseline to that. So we're looking at the velocity of that wave. Okay? Centimeters per second is the units. Again, simple concept. Again, I just need you to know the concept. The numbers I don't necessarily care about, but you do need to know which wave we're looking at. Sorry, my phone's taking off.
Too much technology.
Yes, I agree. Okay.
So that was just a review of the video you uploaded like last week, right?
So that was just the end of the systolic stuff, the Doppler stuff that we hadn't covered yet. Okay.
Are you gonna post another video?
For diastolic, it's already up.
Oh.
Yeah. As of last night. So diastolic is already up there. This is what we're going to talk about today. We will have one more lecture period where we'll discuss whatever we need to discuss. I think we can probably cover diastolic today. Okay? It wasn't very many slides. I think it was only like 29 slides or something like that. The diastolic chart is the thing that you need to know. You need to know that inside and out. If you've got that down, you'll be pretty good for the test.
For the tissue Doppler,
Yep.
did you say that we use continuous wave?
Pulse wave because it's specific site.
Right.
It's range specific.
Is there a reason why there's the primes for the E, A, and S?
So that's a great question. So why do we have the primes on the EA and S wave? The prime will indicate that it is tissue Doppler. Okay? Because we do a lot of comparisons, we're going to talk about that in diastole, we do a lot of comparisons to my inflow of the mitral valve and stuff like that. So because I've already got a nice E wave and I've already got an A wave and the durations and all that kind of stuff, when I take tissue Doppler, they're the same waves. They